Hello everyone. So welcome again to Quantum Club. So tonight we are very pleased to receive Andrea Caviglia. As usually, we give the opportunity for students to give a warm-up talk. And tonight it will be given by Rafael Boeuf-Mendes. So thank you, you two, for giving this. And I want especially to thank a lot Andrea, because he is one of the professors that I think always believed in Quantum Club since the beginning. So thank you a lot for that. You helped us a lot. So yeah, big thank to you. As you have seen before on the slides, we have already prepared the next talk that will be given by Romain Vasseur from Theoretical Physics Department. And it's not here, but we have another surprise that we do not advertise tonight. But if you want to find a hint, go on our website. There is kind of a Easter egg somewhere, so you can understand what it is. So now the floor is yours. So thank you very much.
Okay, well, thank you very much, Elliot, for this kind of introduction, and thank you everybody for coming here. So I'll be doing the warm-up talk tonight, and what I wanted to talk to you about in this warm-up talk is to give you a kind of introduction on what is quantum matter, what is the field of quantum matter physics. So we will first start by introducing what quantum mechanics brings in simple materials, to then go towards two sides of quantum matter. The first one being like the many body interactions between the electrons side with the phenomena like superconductivity. And the other side will be kind of single particle evolution of electrons in momentum space. So kind of topological insulator side. And in the end, I will do a very quick introduction on two approaches for building devices and materials. So let's go right into that. For simple materials, we have that the microscopic crystalline structure of the materials determines the dispersion relation, or what we call the band structure. That is like the energy, depending on the momenta, of the states that are allowed for the electrons to occupy. For simple materials, you have simple band structures, and the interactions between the electrons are negligible. So what we have is that the occupation of these states follow the Fermi-Dirac distribution, and basically at low temperature that means that the electrons will fill all the states at low energy up until there is no more electrons, and this is what we'll call the Fermi surface, that is the occupied states with the maximal energy, and this Fermi surface will determine properties of this kind of simple materials. If this Fermi surface is in the middle of a band, then the electrons will have states that they can go towards if we apply an electric field. So electrons that occupy this kind of states can go on the states above, and that can make a current flow. So this is a conductor, a metal, and if the Fermi surface is in between two bands, then that means that the lower band is completely filled, while the lower band, is completely filled, while the upper band is completely empty, and the electrons have no states to go towards, and there will be no current. So that's an insulator. So this is the very simple picture, but in some materials, depending on their microscopic structure, again, the interactions will not be negligible at all. It will lead to Fermi surface reconstruction. And depending on the interactions, like if we have strong Coulomb repulsion, it can lead to phenomena like Mott insulators, ferromagnets, and a lot of things that I will not have time to talk about right now. And little bit weirder things, if we have an effective attractive interactions, then it will lead to superconductivity and superconductors. So superconductors are materials that when you bring them below a certain temperature, called the critical temperature, they go in a state where there is no resistance at all. You can flow current without dissipation, without resistance. And so this is a very interesting field. This can be seen as the number of Nobel Prize. We have 12 Nobel Prize winners for their work that are linked to superconductivity. And in a more applied way, the fact that we have zero resistance, is really useful to, for example, flow a lot of current. That is useful to make strong electromagnets, and strong electromagnets can be used to make levitating trains or MRIs, all this kind of stuff. But now, one thing that I have told you and not explained at all is this effective attractive interactions, because usually electrons repel each other, like you know. So how does that work? One way that it can work is they go through through phonons, so they use the lattice to exchange their impulsion. So a very simplified picture to show you how that works, I made a small animations, is that you can have an electron that is flowing in this ion lattice, and because it's negatively charged, it will attract the ions. Then it will continue its path, but the ions that are heavy, so they won't go back into their initial position right after. And so if another electrons pass by, you will see this big blob of positive charge, and it will be attracted towards it. And so it will go through that, and the first electrons will have effectively attracted the second one, creating what we call a Cooper pair. That will be the charge carrier in the superconducting current. So this is the simple picture. Now here I've shown a kind of timeline with a lot of different superconductors with their year of discovery and their critical temperature. What I just explained is valid for the most well understood mechanism for what we call the BCS superconductor, and these are this kind of green circle on the timeline. You can see that the superconductors with the highest critical temperature that are around here are not at all like that. This is a different mechanism, what we call the cuprates, the ITC cuprates. The pairing is made by another mechanism that is not fully understood at the moment. But what we know is it's again very linked to the microscopic structures, and it's linked to it happens in the copper oxides planes, because, well, this type of cuprates, they can have different structures, but what they have in common is this type of copper oxides plane that are right here, that I've shown you an example of one of them here. And so, yeah. That was all for superconductivity. Now we can go through we can take a step back and go to the single particle evolution in momentum space. And to understand that, the first thing we need to talk about is what happens when we're working in a curved space. So to understand that, we will take a step back from quantum matter and imagine a vector on a sphere. And if we try to move it on the sphere by keeping it flat on the ground, we can make it do a small path, a closed path, and you will see that in the end, what happened is the vector gets rotated. At the beginning, it was pointing that way, and now in the end, after this closed path, it's pointing another way. It's like a force acts on it if you completely ignore the sphere, but it's not really a force, it's just linked to the curvature of the space you're working on. And the same kind of things can happen to electrons that are evolving in the momentum space, in their band structure. What happened is the wave function fill what we call the Berry curvature of the band that we describe by this letter omega. And this has for consequence to add a term in their velocity, what we call the anomalous velocity, that is given by the cross product of the electric field and this Berry curvature. So you can see that it looks a bit like a magnetic field, and in some sort of way it is kind of an effective magnetic field. So that means we can have Hall effect even without this magnetic field. Electrons can drift if you put an electric field in a sense, in a direction, then the electrons will drift, an Hall effect. And we call that the anomalous Hall effect. Even more interesting things happens when this kind of non-trivial Berry curvature happens in an insulator. Because in that case, what we can define is this number, C, that is the integral of this Berry curvature, what we call the Chern number, and it will always be an integer when working with an insulator. And in that case, what you have is that the whole conductivity will become quantized. So C, this integer, times the quantum of conductance, E squared over H. But the longitudinal conductivity, because we're in an insulator, is completely zero. That means that when you apply an electric field, you have no longitudinal current, but you have a perpendicular current that appears. Even more interesting, you get dissipation-less edge states. That means that at the edge of your sample, there will be electrons flowing on one side in one direction and on the other side in the opposite directions. And these edge states are topologically protected, meaning that you can't destroy them with local perturbations. If you act on this side of the sample only, you will never break these edge states or the other one, and same thing with the opposite. This type of materials have a lot of applications, can have a lot of applications in nanoelectronics or spectronic devices. They could have potential use for topological quantum computing. There has been theoretical prediction of this type of edge states that could be used in quantum computing because of their because they're immune to local noise. It is very interesting to avoid some kind of errors. There has been claims that this type of edge states has been observed. This is the famous paper that you may have saw from Microsoft, but I mean, the claim is, well, shaky, to say the least. And this also can be used in metrology because of this quantized all conductance. You can define standards for resistance. Now, to talk about practical, how do we build materials and devices? There is kind of two main approach. Either the top-down approach, which is the usual approach of taking a big materials and cutting and refining it from the big piece to get what you want, the device that you want. But another approach that is maybe more interesting is the bottom-up approach, where you build the material from scratch at the atomic level using like elements from the periodic table, and that way you can tune its structure and its properties. That way you can build new materials or control the microscopic structure of said materials. And this is very useful to study or tune this kind of exotic quantum phenomena that I told you about in this matter. That was all for me, for the warm-up talk. So now time for the main talk. Thank you very much. The floor is yours.
So let me start by thanking the Quantum Club. As you have heard, I'm a big fan of the Quantum Club. I think it's fantastic that you guys are self-organizing these great scientific activities, and you put in a lot of effort also in the outreach part. And so for me, it's a really great pleasure to contribute to this series of events. So let's start by staring a little bit at this nice video made in Geneva by Xavier Ravinet. So towards the middle of the talk, I think you will have a little bit of an idea of what this is trying to represent. So for now, just notice that this is trying to represent an electronic wave function. So this is an electron that has a certain spin, and the electron is a wave packet that is moving in a two-dimensional material with a certain hexagonal structure. And as you can see, is moving through a medium that is active. So the electrons, by moving throughout this medium, is generating some back action, and this is generating some nonlinearities in the responses of this material. So this is trying to describe that matter can be a very active medium for the transport of electrons. So 2025 has been a special year for people interested in quantum. So the UN declared this the International Year of Quantum Science and Technology, and this has catalyzed a lot of outreach activities. In Geneva, we've been very busy with those, and it's been fantastic to have the collaboration of the Quantum Club for almost all of these activities, right? So we started early with a big conference for the large public made by Julien Bobroff, that surprised us with some unconventional ways to talk about physics without PowerPoint. So this is a nice approach in which with a boîte d'allumettes He was describing a lot of interesting physical phenomena, and the Quantum Club helped us a lot with the promotion. Then we had the Nuit de Musée. That was a fantastic success, where all the labs were open, and a very large public was attracted, and that was something that had an impact in the local community, really. And let's not forget what we did at the museum. So in front of the museum, we had this beautiful exhibition of scientific pictures made by our section. And in the museum itself, we had a very nice exhibition, and this is a photo from the vernissage. So that was a very nice experience as well. And then last but not least, the Pint of Science. Everything that was done to connect and get people excited about science in the places where they go. And so for this, a big thank you to the Quantum Club, and let's continue the collaboration. I think it's going really well. So now, my talk. So all these outreach activities made us think a lot about what is quantum and how to communicate with the public in some kind of a efficient manner. What are the main features that we want to highlight to the public about quantum? Quantum is a complicated subject, and there are various ways to approach the problem. The way that I personally like the most is the following. For me, quantum is a story of two vacua. There's the classical vacuum. So in the classical vacuum, we have a perfect void. So there's a perfectly empty space with no matter, there are no charges, no currents. Okay? As a result of this, there are no fields present in the vacuum, and these zero fields that do not fluctuate. So this is a perfectly steady situation where there's no energy density associated with any field. Okay? So that's the classical vision of the vacuum. Quantum mechanics completely changes this picture. So that's, in my view, this is really the big departure of quantum in our understanding of the world. In a quantum vacuum, we have the ground state of quantum fields. Okay, so this means that we have fields that have a zero mean, but non-zero fluctuations. So there are indeed fluctuations happening at equilibrium in the quantum vacuum, and each mode of these quantum fields is carrying a 0-point energy of half the frequency of this mode. Okay, so this is really something that is a radical departure of the quantum vision from the classical world. When I first heard about this, I was very skeptical. So, how can you believe that in vacuum you have this stuff? Right, so you should be skeptical, and you should ask for some experimental evidence. Okay, and so I'm going to give you 3 examples of experiments that tell you that this may actually be happening. First example, the Casimir effect. So if you take 2 metallic mirrors, you make sure that you have no excess charges in none of these mirrors. These are perfect mirrors. In the classical vacuum, you take 2 mirrors, you bring them next to each other, and they're static. Nothing happens. They don't attract each other, they don't repel each other, everything is static. There's vacuum in between. In quantum mechanics, this ceases to be true. In quantum mechanics, you have quantized electromagnetic radiation in and out of this two mirrors, and within the mirror, you create a certain set of discrete quantized levels for these quantum fields, and as a result of summing up the energies of all these modes, you get a net force. So the 2 mirrors in the idealized case, they would attract each other. Okay, and they would attract each other with a specific power of the distance between the mirror. So this is something that you can verify experimentally, and this has been done. So neutral mirrors in vacuum attract each other. Casimir effect. Second proof, the Purcell effect. In quantum mechanics, you know that you have a phenomenon called spontaneous emission. So if you excite an atom out of its ground state in some excited state, it will have a finite probability of decaying back to the ground state. Okay? And the rate of this decay is determined again by the interaction of this 2-level system with the quantized vacuum. Okay? if you now place an atom inside of a cavity and you change the nature of the modes present in the vacuum, the spontaneous emission can be accelerated. So by placing the atom inside this cavity, you will see a faster emission. Okay. Then this depends a lot on the details of the interaction between the atom and the mirrors. There are cases in which this can be decelerated or accelerated, but in the most simple version, this is an acceleration effect. Okay, so this vacuum is doing something to the process of spontaneous emission. Third experimental proof, if this is not enough, the Lamb shift. So if you take a hydrogen atom in vacuum, you will have a certain transition energy between the n equal 1 state and the n equal 2 states. Okay? If you consider this problem in the Schrödinger equation level without a quantized version of the electromagnetic field, the S level and the P level are degenerate in the same energy. Okay. In reality, if you consider the fact that you have a quantum field that is around your hydrogen atom, then you will have a shift of these two energy states of the order of 1,000 megahertz, of a gigahertz, so in the micro electron volt range. So it's a small shift, but this is measurable. So the vacuum is the QED version of the vacuum. So this has a lot of consequences. So classical vacuum, for our understanding of matter of materials. So in an equilibrium situation, materials in a classical vacuum are just boundary conditions. They're static, they're boundary conditions, and there will be some electromagnetic responses or observable things only when I drive the system. Okay. But in the quantum vacuum, materials are much more interesting. So now materials are not just static boundaries, but the materials are reshaping the spectrum of electromagnetic modes present in the vacuum and their fluctuations. Okay, so just by placing mirrors close to each other, it's possible to change material properties themselves. So the materials are changing the vacuum, and the vacuum is changing the materials. So materials are not independent objects that I place in vacuum, but when I place object in vacuum, I have a network of relations that form. Okay, so they're not, when I assemble matter, I'm not taking static pieces that I put next to each other, but the static pieces, they naturally form a network of relations. Right, and that's our motivation for building matter one atom at a time. So this is why we go through the trouble of taking materials that are quite complex and have a lot of atoms in the unit cell, and we place them one atom, one unit cells, one layer of atom at a time. So the image that you see here is an electron microscopy image acquired in a sample made in our lab. Each bright spot that you see is an individual atom. So there is a column of atoms that is going through the wall here. Okay, so here you see a projection. And so each bright spot tells you what type of atom you have in the structure. Here you have very heavy atoms, so they shine very brightly in these maps. So you have in this material strontium and iridium and oxygen. And the other material you have strontium, titanium, and oxygen. So each layer of material here has been deliberately placed by an experimentalist, so in a controlled manner. It's a little bit like playing Lego, but at the atomic scale. So this is my daughter Beatrix doing an experiment, but here I would like to underscore a fundamental difference between Beatrix experiments and this experiment here. So when she places a yellow brick with a white brick, the yellow remains yellow, white remains white. So these are static brick in a classical world. Okay. In a quantum world, when you place yellow next to white, you may get a completely different color. Okay, so these are not static bricks, right? And this goes back to what I was telling you before. So we are not dealing with materials that are static boundary conditions, but are materials that are shaping their environments and that are shaping each other. Okay, so the Legos are shape-shifting, if you want. So creating interfaces between quantum materials create interesting boundary conditions for electrons. So this gives us an opportunity to create superposition states between different orbital states, for example. This is an interesting way to create boundary conditions for electrons and create new states of matter. Additionally, interfaces of quantum materials allow us to create boundary conditions for photons and phonons. So we can create so-called electromagnetic cavities in which we confine the dynamics of photons within a very narrow layer. And here we can even create mixed states of matter where photons and phonons become a hybrid object called a boson. So as we just heard in the warm-up talk, the band structure of materials is important, and at specific point in the configuration space of these quantum systems, which is the momentum space for a crystalline solid, we can create quantum superpositions of different orbital or spin states that have new and interesting properties. Okay. And the way we characterize these phenomena, when we bring everything together, from a theoretical standpoint, we want to create descriptions of local interactions, including various mechanisms of symmetry breaking, leading to local Coulomb repulsion, hopping integrals, spin-orbit coupling, and magnetic exchanges. But not only this, we were also influencing the local structure of the electronic wave functions. And this is described, as we heard before, by geometric quantities called the quantum metric and the Berry curvature. And I will tell you a little bit about that. But before I go into some examples of taken from my research, let me just take a step back and why are quantum materials interesting? What are we dealing with? Right. So when I talk about this, I try to go through different levels. So at first level, you can say a quantum material is something that has interesting properties that you need quantum mechanics to describe. Right. So something like a superconductor, a material whose electrical resistance drops below a certain temperature, and at the same time completely expel a magnetic field from its interior. So that's an old example from a discovery on 1911. A more recent discovery of a quantum material is a topological insulator from 2005. So this is a material that is insulating in the bulk, but possesses some conducting states at its boundaries, and these states have a guaranteed protection from external perturbation, as we heard about before. Yeah, but now let's go a little bit deeper. So all these properties arise from having a structure of the wave functions, and this touches a little bit, what is really quantum. I used to be a little bit more radical about this, and wave functions are stuff that you just use to calculate. But quantum materials create a situation in which the structure of wave functions is really giving rise to measurable phenomena. And I think the most known example is entanglement for a two-particle system. So Einstein didn't like this phenomenon at all, and now we clearly have to account for this in our understanding of nature. And going a little bit more in depth, what type of structures can we classify in quantum materials? From my perspective, there are two main families here that we are dealing with. So when you're dealing with a many-particle system, so you have collective quantum phases of matter, you have quantum entanglement of a many-body wave function. Right? And a second interesting scenario is when you have single-particle physics, when you have geometric and topological matter, you have the quantum geometry of single particle wave functions that is important here. And I will tell you a little bit about how this arises. So the first example, the superconductor, is clearly an example of a many-body wave function. So this is a coherent state of Cooper pairs in the most simple description of superconductivity that we heard about, the BCS theory. So here you have a many-body wave function that respects the antisymmetric relations from the necessary statistics. And this many-body wave function has a structure that leads to these macroscopic measurable properties. A topological insulator, as we heard, is a little bit more subtle. So here we have wave functions where the spin of electrons is constrained to be always perpendicular to its momentum. So this is called spin momentum locking, and it arises from these geometric properties of the wave functions. And in our lab, we like to build these complex materials atomic layer by atomic layer and combine materials with different properties to form a single crystalline structure. And so the reason we do this is because at interfaces we can create new states of matter with even more interesting properties. And I would like to give you a little bit of flavor on how we do this and how this works in the lab. So what are the key enablers and what allows us to do this type of experiments? So we call this work epitaxy. So epitaxy is about synthesizing materials with a certain crystalline form with a compatible crystal on top to create a single crystalline material. And the starting point of this type of experiment is having a very flat surface, indeed an atomically flat surface. So we stand on the shoulders of giants, and since the early 90s, people have developed chemical methods to create complex crystals with an interesting stoichiometry with a single atomic termination. Okay. So this is quite remarkable. So this is an object in which you have, for hundreds of nanometers or microns, a completely flat surface where the rugosity is below a single unit cell. And then you have one single unit cell steps. And then you start again for 1 micron. Okay, so if you think about it, this is a very crazy starting point. Then, having this type of crystals available, then we can grow something interesting on top. Okay? And we use techniques that allow us to deposit single layers of atoms on top of our substrates. So this one is called pulse laser deposition. So we use a laser to create the atomic cloud that then is going to deposit. And during the deposition process, we can use an electron beam to probe the growth process. So we can follow these atoms coming into the surface, arranging themselves to create a perfectly flat structure. And we see this by following oscillations of the intensity of a diffracted electron beam. So this is something, so it allows you to really count the number of layers of atoms that you're putting on top of a crystal. And the new kid on the block is the hybrid MBE approach. So this is something that we have built here in Geneva, and we started working with it. So it's an innovating way of building materials that is based on molecular beams. And this would allow us to have very exquisite control on the stoichiometry of these materials and to minimize the number of defects, to have interfaces that are absolutely atomically perfect. So this is our playground. So on top is the materials that we like to grow, and on the bottom is the substrate that we like to use as a function of the lattice parameter. So as you can imagine, we are growing a cube on top of a cube. So we would like to find for each material to find a substrate with a similar lattice parameter to minimize the amount of strain that we are imposing on the material. And you see we have a nice span of all this phase diagram of a number of interesting materials. So here you have a ferroelectric, here you have a material with a very high electromobility, here you have an antiferromagnet that is of a Mott insulator, another Mott insulator, a ferromagnet with very curvature, and so on. So all these are quantum systems with a lot of very interesting properties to study. All right, so this is our playground, and I'm going to give you 3-4 examples of stuff that you can do with this. First example, superconducting interfaces. So some of these materials are insulating, but as I told you before, these Lego blocks are dynamics. So when you take some of these insulators and you bring them next to each other, they completely change their properties. Okay. This is an example of 2 insulating materials, strontium titanate and lanthanum aluminate. So these are good insulators in the bulk. So 3.2 electron volt band gap, 5.6 electron volt band gap. So very good insulators. You bring them next to each other, and automatically at the interface you get a 2-dimensional electron system of metallic electrons. Okay. So this was already a fantastic discovery in 2004. But these electrons are not only metallic, they're also superconducting. And this was discovered in Geneva here in 2007. Okay, so out of 2 insulating materials that do not conduct electricity, you get a superconducting layer. So the opposite property, if you want. And these superconductors at oxide interfaces, they have a lot of unusual properties. So first of all, you have an extremely low concentration of Cooper pairs. So we heard about Cooper pairs, the elementary actors in the world of superconductivity. In these systems, you have as few as 10 to the 11 Cooper pairs per square centimeter. Okay, so this amounts to only a few Cooper pairs per coherent volume in the system, which is a very interesting limit to study superconductivity. Because the superconductor is so dilute, you can apply a gate voltage, like in a field effect transistor, and you can switch on and off superconductivity. So you can increase or decrease the number of carriers in the system, move the position of the chemical potential, change the mobility of the electrons, and you go through an insulator to superconductor transition by switching with a switch. You go from zero resistance to a finite resistance by flipping a switch. Okay, so that's another interesting property that you get especially at this interface. And now one of the latest results from our group here. So there is a new superconducting interface based on another interesting material called potassium tantalate. So this is a material that is never superconductor in the bulk, even when doped. But at its 111 surface, it shows a very robust superconducting state with a critical temperature that can be as high as 2.6 Kelvin. And this is a discovery made by Ulrich and Arun here. Here I'm showing the data that is still unpublished. So this material is extremely resilient to magnetic fields. So this superconducting state can survive up to magnetic fields that are approaching 50 Tesla. Okay, so and in order to have this extreme resilience, you need your magnetic field to be perfectly parallel to the interface. As soon as you move a little bit from perfect orientation of your field, your critical field decreases in this V-shaped curve. Okay, so this is an extremely resilient superconductor with a pairing mechanism between the electrons that is still not fully understood. Okay, which is something that can only be realized at this oxide interfaces. Second example, engineering quantum geometry. Okay, everybody's taken quantum mechanics. We're in the quantum club. All right, so you surely have your favorite Hamiltonian. All right, so imagine that this is your favorite Hamiltonian. Rush Hamiltonian, something with I need to get a two-level system out of it. All right, so you diagonalize this Hamiltonian, you get your spectrum, you get your eigenstates and eigenvalues. Okay, so the eigenstates in your configuration space will form some kind of vector field. Okay, so your system will vary as a function of some parameters, let's say momentum, or it can be any parameter you want. This will form a certain vector field. The global variations of this vector field will describe topological properties. Okay. So this will give rise to topological invariants, such as the Chern numbers that were introduced by Raphael. But this vector field will also have some local changes. So the local changes of these quantum states in configuration space are described by an object called the quantum geometric tensor. Okay. One of the elements is the Berry curvature that was introduced by Raphael, and the other element is the quantum metric that describes the distance between the states. So how does this geometry come about? How does it come naturally? Well, I think it's quite direct to visualize this if you realize that this vector field here is also a map from configuration space to the complex projective space of your system. So for you know the two-level systems. So for a two-level system, this is the Bloch sphere. So for each position of your configuration space, you're defining a certain spot on your Bloch sphere. Okay. But in the Bloch sphere, we have a distance defined between states. So this is one minus the distance between two infinitesimally close quantum states. Okay. So the scalar product is giving you a very nice direct way to define a distance in the complex projective space. But now, by virtue of having here a texture, some vector field, you can pull back this metric in the configuration space by this very simple operation. Okay, so this allows you to define very directly a distance between states in configuration space. And this was realized for the first time by Anand and Aronoff in 1990, that proposed a completely geometric formulation of quantum mechanics based simply on geometric quantities. And the two key quantities at hand here are the distance between states and the local curvature in configuration space, the Barry curvature that was nicely introduced by Raphael. Okay, together they form the so-called quantum geometric tensor. Okay, and for a two-level system with a certain spin texture, there is a very direct formulation for the Barry curvature, and what we discovered recently, and there is a similarly very direct way to define the quantum metric for a two-level system. And this gives rise to important measurable quantities. So from the Barry curvature, you heard about the anomalous Hall effect, the quantum Hall, the Chern insulators, and topological states. But the quantum metric, that only been recently discussed in transport experiments, you give rise to nonlinear transport and new type of light matter interactions. Okay, and recently in our group, Giacomo has emphasized that through the quantum metric, there is a new type of nonlinear magnetoresistance that occurs in very specific configurations of magnetic field and currents in your sample. So this is called quantum geometry. It's based on a quantum superposition of quantum states at finite crystal momentum. So it could be a superposition of orbital states, of spin states. But this technique allows us to define curved spaces where new properties emerge. And so this was the idea behind this nice animation made here by Scientify. Very good. How much time do you have left?
We still have 15.
No, perfect. Okay, so then let me give you a couple more examples of cool things that you can do with oxide interfaces. And this has to do with dynamical properties. So this is the expertise of Tobia that is present here. So I told you about phonons. So this is a quantum field that will have some 0-point fluctuations, and will have some thermal excitations whenever you have a material at finite temperature. Okay, so phonons, so crystal vibrations in your material, will never be completely quiet. So phonons will always have some chaotic motion in equilibrium conditions. All right, so this is the natural state of a crystal lattice. It turns out that if you prepare a laser pulse that is tuned in resonance with a specific phonon mode, you can impart a very specific dynamics in phonons. If you come with a pulse of electric field through a beam of light that is tuned at a specific phonon resonance, so they have a specific frequency, you can impinge a certain dynamics, you can trigger a certain dynamics of your crystal lattice. Now, if you want an image, it's a little bit like an orchestra conductor that gives you the starting point for some coherent collective dynamics. All right, and so this is the whole story of light-driven phonons. So by using mid-infrared laser pulses, we can excite materials out of equilibrium, and if we do it with a strong enough electric field carried by your excitation pulse, you can generate a crystal structure out of equilibrium that would not exist in the material otherwise. So you can create atomic arrangements that live for a certain amount of time in an out of equilibrium state where your materials start to have new properties. Okay. And in these experiments from a few years ago, so this was 21, we demonstrated that using this laser pulses tuned in resonance with a phonon mode, we could turn a material that has no magnetization into a system that has a certain magnetization. So we could generate a transition from an antiferromagnetic state that has no net magnetization to a state in which the material develops some magnetization. So we magnetized a material by shaking its crystal lattice. right? So we call this phono control of magnetism, and it opens interesting perspective for non-thermal lattice control of magnetic interactions. The other example that I wanted to give you for light control of materials is the generation of spin waves. So in the same material, again, by using laser pulses, we were able to induce for the first time the first ballistic antiferromagnetic spin waves propagating at supersonic velocities. So this is by impinging on the material a certain laser light that was exciting on a very narrow region the surface of the materials and the spins of the materials. We could induce an oscillations of the spins that would propagate inside the material over macroscopic distances in the orders of microns with a ballistic character. So this is a coherent propagations of angular momentum, which is important for an emerging field called antiferromagnetic spintronics. And again, this is made possible by having this specialized surface that has specific interaction with light. And now the new direction of research that is very important for us are light matter hybrids. So what I've shown you so far for light matter interactions are all driven situations in which we bring photons into the picture and we shake the system out of equilibrium. But as I showed you before, these quantum fields, they can interact even in the absence of an external drive. Okay. So what we are working very hard towards with Tancredi and Tobia is to build light matter hybrids. So situations in which a cavity mode is hybridizing with the phonon modes, and by doing so, there are theoretical proposals that indicate that it's even possible to drive phase transitions in materials. Okay, so this would be phase transitions that are controlled by fluctuations of the vacuum of the electromagnetic field. Right. So the key aspect that bring together all these experimental activities is the fact that we are controlling the energy landscape for electrons, spin, and phonons, and this allows us to create new properties. So that's why we build quantum materials one atom at a time. All right. So these are the references that I discussed today with you. Let me highlight the people that are working towards these projects. In particular, here there's Tobia. I highlighted also the work of Tancredi and the work of Giacomo, and also the work of Arun and Ulderico. I would also like to acknowledge the collaborations with our theory friends. So we have a lot of interactions with theorists that allow us to model this type of phenomenology. And let me conclude by the take-home message. So the emerging picture from quantum mechanics is that the quantum world isn't made by particles in an empty void. Okay, so we find relationships all the way down that are mediated by fields. They have a ground state that is already active in vacuum. And by engineering interfaces, cavities, and lattices, we're not just arranging static pieces of matter, we are actually shaping the medium that is making this relationship possible. And this allows us to create new ground states and new possibilities. So if you want to have one word of wisdom, so in a world made of relations, wisdom is the art of composing better ones. So this is my final message. Thanks.